All right, hola mi clase. We are doing 6.2 exponential functions, so I can use properties of exponents to solve equations with rational exponents. So that's why we did 6.1 of properties of exponents, because we're moving into exponential functions. So the key terms we're going to talk about and start to look at are, the first one's called an asymptote. Okay, so that's how you say that word. It's asymptote. It's a line where a function approaches but never touches. Like, it's an imaginary line that a function gets really close to, but will never touch and will never cross. I consider it similar to our line of symmetry when we did absolute values, but this will be a line where it never touches it, where absolute values, it did clearly touch it at the vertex. So it's similar to that. It's like a dotted line that's imaginary. A constant ratio is a ratio that is the same for the consecutive y values in an exponential function. So remember, a ratio is like a fraction. It's the a over b, and we're going to specifically look at the consecutive y values. Okay? And then an exponential function is the product of an initial amount and the constant ratio raised to a power. Okay, so it would look like this. F of x, there's our function notation, equals a, our initial amount, times b, our constant ratio raised to the power. And notice our power is the x. Our x is our exponent, and so it's going to actually change. And that's why this becomes an exponential function, because the exponent continuously changes. All right, so here is our first one. It says, what does the graph of f of x equals 2 to the power of x look like? And then what I did is I gave you a table that we're going to fill in together. And then we're going to graph it to the best of our ability to, because some of these might be a little difficult to graph. So the first one is -2. So we'll take 2 and raise it to the -2. Now this is where our exponent properties come into play, because remember, negative exponents actually make us take the reciprocal and then raise it to the power. So it would look like this: 1 over 2 squared, which then equals actually 1/4. So then we're going to do the same thing here. We're going to go 2 raised to the -1. Again, it's negative, so we take the reciprocal, 2 raised to the first power, which is then 1/2. All right, 2 to the 0. So we haven't really fully talked about this, but it has come up on some of your quizzes. Anything raised to the 0 power is just 1. Anything raised to the 0 power is 1. All right, 2 to the first power, that is 2. It's just itself. 2 to the second power is the same as, right, 2 times 2, so we would get 4. That's a really bad little exponent. I'm going to fix that. And then 2 to the third power, remember, is 2 times 2 times 2, which equals 8. So now we have our points: -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. So we're going to do our best to graph these. So -2, 1/4 is going to be really close to here. And then we have -1 1/2, so that's about there. We have 0, 1, 1, 2, 2, 4, and then actually 3, this is 5, 6, 7, 8, kind of fits, but it's kind of slightly off our grid. It's up here. You'll notice that this is making a curved situation. So when we connect our dots, we're going to actually curve them. An exponential function is a curved line. We are not going to make straight lines, and we're going to put an arrow on the end. And then here, we're going to actually go like this, and we're just going to get as close and go like that. It is actually never going to cross the 0, y, or x-axis. So in a sense, our asymptote, where it's going to get really close but never cross, would actually be our x-axis. Because what it's going to do, let's think about that. If I try to do like -4 or -3, it would become an 1/8. And then -4 would become a 16th. It will always be a number. It just won't be and ever go below 0, right? It'll be a smaller and smaller and smaller and smaller fraction, but will always be a fraction of some kind, even if it's 1 to the, thousandths. It's still a fraction. So this is that asymptote. The line that will never, never, never cross, right? So that's where y equals 0. It's that x-axis. All right, so we've got a network administration uses the function f of x equals f5 to the x to model the number of computers a virus spreads after x number of hours. If there are 1,000 computers on the network, about how many hours will it take for the virus to spread to the entire network? So you'll notice we don't have any negatives. Well, that's because we're talking about hours for our x, and there is no such thing as negative hours. So we're not going to have anything over here. Our graph's going to be all in this first quadrant, our positive group. So we are going to start with 5 raised to the 0 power. That gets us 1, right? An initial computer has been infected, right? 0.0. 5 raised to the first power gets us 5. So that means 5 computers have now been infected in the first hour. 5 to the second power gets us 25. So 25 computers have been infected now in the second hour. So you can see how this is exponential, right? Because once 1 gets infected, that 1 infects 5 more. So you can see how it continues to grow and grow, sorry about that, exponentially. All right, so 5 to the third power is 125. 5 to the fourth power is 625. And 5 to the fifth power is 3,125. So you can see these grow really, really, really fast. All right, so we're going to graph these. So again, we don't have 0, 0, we have 0, 1. So there's our first one. Let's actually even make these go by, I don't know how we're even going to graph these because they're going to jump really, really, really fast. This is not a great graph for this. So we'll make these go by 100 just because these are going to jump really fast. So 100, 200, 300, 400, 500, 600, and then this one would be 700. So to graph 0, 1, we'd have to like basically put it almost on that 0, 0 spot. And then same 0 or 1, 5, is barely above that. They almost are going to look like they're in the same place. Right? 225, still not even halfway. We're basically here. I mean, these are really hard to graph, right? They're so small. Then it starts to jump. So at 3, we can actually come up here at 125. And at 4, it jumps to 625. So you can see this is a huge jump. Okay, so it starts out and almost looks flat, right, to what we would call the naked eye, and then it starts to jump very quickly and very fast. So there's our graph to the best of what we can do with our hands, right? Now it does say if there are 1,000 computers in the network, about how many hours will it take the virus to spread to the entire network? It says about. So it says we know that somewhere between 4 and 5 hours it happened. Okay, so this is at 625. We want 1,000. So it's probably closer to 4 hours than it is 5 hours, because at 5 hours it's 3,000. So it's probably pretty small. So we could estimate, at about 4 4 and let's say like 3 hours, 3/10 of an hour. And I know I just totally wrote that crooked. Okay, but it's just an estimate, okay, that it'll reach 1,000 computers at about that time. Somewhere between 4 and 5 hours. Because 1,000 is closer to 625, we know it's probably closer to that. And so that's why I estimated it kind of at a lower decimal. All right. So now what we're going to do is write an exponential function given the data. Okay, so before we were given the exponential function and we made the graph. Now we're going to take the data and write one. So remember, A is always our initial amount. Our initial amount is always where it's at 0. Okay, so this is A. B is our constant ratio. If we look back at our vocabulary, the constant ratio is the ratio of just the y values, one after the other. It said consecutive, so it would be this ratio. So for our checking this, we're technically from here to here, we're checking 12 divided by 4, and we're getting 3. And then we're checking this consecutive ratio, and we're going to do 36, except I didn't write 30. We're going to do 36 divided by 12, and that would also get us 3. And then we need to check this consecutive ratio, 108 divided by 36. If you type that into your calculator and actually divide, it is also 3. Okay, and then technically we should check this consecutive ratio, so 324 over 108, and it will also be 30. So our consecutive ratio is these 3's right here. Okay, that's our consecutive ratio. This is equal to B. It's the same constant ratio happening every single time. All right, so now that we have our A, 4, right, and our B, 3, we can fill them in. So our function would be f of x equals 4 times 3 to the x. And that's actually it. And the reason that is because exponents come before multiplication. So to find and do this further, we would actually have to take 3 to the 5th, right? That would be the next one. And then times it by 4. And we do 3 to the 6th and times it by 4 because exponents are before multiplication in order of operation. So I cannot multiply these and just say it's 12 to the x. It doesn't work mathematically. This is it. We are done. All right, so this time instead of having it in kind of a nice table, they gave us into in points, but it's no different. This is my table just written in point form. So it says write an exponential function for each set of points. So again, at our 0 is always our A. So here's my A. And then remember my constant ratio. All right, I'm going to do problem A right here. Is my consecutive y's. I only care about the y's. So the first one would be from here to here, and so it would be 12 divided by 3, which would get me 4. And then my next one goes here to here, so it's 48 divided by 12, and that actually gets me 4. And then I would do it again, 192 divided by 48. If we put in a calculator, it will get me 4. And then here, 768 divided by 4. Not 4, 192. 192, it will get me 4. So now I have my B, there it is, it's 4. And since I have my A and my B, I can write my function. So be f of x equals 3, that's my A, times 4 to the x. There's our function notation for problem A. All right, so problem B, you're actually going to do yourself, and we'll go over it in class. Consider it your independent practice because there isn't one. So you're going to do B, and you're going to write it like this, and you need to check these constant ratios and find your A. All right. So it says Talisha is offered 2 pledges for donating to a charity. Which option will increase the pledge amount faster over time? So option A is that at the first week we get $100. Okay, so that's that's going to be considered our initial amount. After that, each week the amount is going to increase by 25. So what we're going to do is take this and we're going to add 25, and so we'll get 125 here. And then we'll add 25. It's just increasing by 25. Okay, so 150, 175, 200, 225. Okay, so all I'm doing is adding 25 each time. Now, option B says on the first week, you're going to get $1. And then each week after that, the amount is going to triple. Tripling is actually timesing by 3, right? So our initial amount is $1. We're going to take that and times it by 3. So we're going to get $3. Then we're going to times by 3. We're going to get $9. And we're going to continue to do that. 9 times 3, 27. Right? Calculator it. 27 times 3 is 81. Calculator it. 81 times 3 is actually 243. So, which option is increasing my pledge amount faster? It's actually option B. Because if you look at 5 weeks, I'm at 225, I'm at 243, I'm actually already over the other one because it's an exponential amount. If we go to next one, 6, it's going to be even more. So option B is the option that increases your pledge at a faster amount over time. Okay, and it's because it's exponential. We're multiplying instead of just adding. All right, so the things to remember, right, is that the function itself, you should probably memorize that. I think that's our biggest issue, is that it's f of x, a times b to the x. And this is our initial amount. And this is our constant ratio. All right. Until next time, adios.